Welcome, everyone. We are here in the VLab seminar, and today we have Ood Shabtai from Tel Aviv University, who will speak on pairs of spectral projections of spin operators. You are very welcome, Ood, and let's enjoy your talk to everyone.
Thank you very much for the opportunity to speak here in the seminar. I'm really happy to speak here. Okay, so I will start. I'm starting with some sort of basic stuff to fix notations and everything. So I talk about spin operators, which are, generators of. So they are a generator of SU2 of the group. So I will start with some slides of preliminaries. So first of all, I will Lie algebra, just vector space over R with Lie bracket. So I'm sure it's very familiar to all of you, and we require the Jacobi identity to be satisfied, and then we will consider representations of Lie algebra. So representation is just a linear map from the Lie algebra to the endomorphisms of some vector space, which respects the bracket in the sense that it takes a bracket of elements of the Lie algebra to just a usual commutator of linear operators. And we say that the subspace of this V of is invariant under the representation if for every element of the Lie algebra and every element of the subspace, when we act with this element, we get an element again in the very same subspace. And then we will say that the representation rho is reducible if the only invariant subspaces are the trivial ones, namely the zero subspace in the entire space. Yes, and also I should say, of course, please stop at any time for questions, so on, comments, and anything. Okay, so this is a slide about real algebras, and now the actual Lie algebra, which will be of interest to us. And this is SU2. So we can just specify a basis, right? It's a vector space. So we can just specify a basis. Here it is given by this sort of up to normalization, the Pauli matrices. And the Lie bracket is just a commutator of matrices here. And then so these three matrices satisfy this rather nice commutation relations. And any triplet of operators, linear operators, which satisfy these commutation relations, define the representation of this Lie algebra just by mapping the basis of the Lie algebra to this triplet of operators that we found that satisfy this relation. So these relations are really important. And okay, now what about the representation theory of this Lie algebra SU2? So the representation theory is quite simple and nice. Basically, for every natural number, we have a unique up to equivalence, irreducible representation of this Lie algebra SU2. And then we can assume that the presentation acts by skew symmetric operators, or equivalently that I times the representation, so it gives us a Hermitian operator, self-adjoint operator. And then there are standard realization of this rho D, of this d-dimensional irreducible representation. So the one standard realization is on bivariate homogeneous polynomials, which maybe you've met, and then there is the standard realization on spherical harmonics. There the dimension is off. So these are just really the standard realizations. And then now we can define the sort of main object of this talk, so the spin operators. So they're just given by the image of the representation of the basis element. So J1, J2, and J3. So them I will call as spin operators, and then they satisfy the commutation relations written here. And I mean, these are of course the same commutation up to multiplication by I of the basis of the SU2, the basis element. So these are the spin operators, and what is important for us to keep in mind is the spectrum. So the spectrum can be derived just by using the commutation relations and reducibility, by using raising operators and lowering operators, which is a classical argument, so to speak, and they have the same spectrum. So if the dimension is D, so we introduce this new parameter J, which can be a half integer, possibly, and the spectrum of this operator J1, J2, and J3 is given by the set sigma D. So the eigenvalues are going from J, J minus 1, all the way to minus J. Okay. So right, so this is the first, so this is really the main thing. And then what I will do is that I will compare projection on subspaces spanned by eigenvectors of spin operators with random projections. And for this reason, I will now specify some preliminaries about random projections. So, so we have the Grassmann manifold, which is just a collection of k-dimensional subspaces of Cn. And it is a sort of a nice manifold, a smooth projective variety, and it has an action of the unitary group, which acts by taking a vector space. Well, we take a unitary operator and act in vector space to a vector subspace to obtain a new subspace, and we have a measure which is invariant under this action. So okay, so we let mu k n denote the probability measure invariant under this action, so to normalize, and we will identify a subspace or a point in the Grassmann manifold with the orthogonal projection of the subspace. So this will be our source of random projection. So just a Grassmannian equipped with this probability measure. Okay, so now I think indeed we can talk about the main, really the topic of this talk. So yeah, so I consider polynomials in two spectral projections, so bivariate polynomials. So first, let us consider the formal object. So the formal object is just complex unital algebra generated by this non-commuting variables. So this is of course important in our story, and we require them to satisfy the relations of projection. So x squared equals x, and y squared equals y. So this algebraically represent to us projections, and now for the question. So here I'm denoting P1D and P3D, a pair of spectral projections of spin operators. So these are orthogonal projections of the subspaces spanned by eigenvectors of J1 and J2 respectively, and corresponding to eigenvalues with positive eigenvalues. Okay, and then we consider this sort of polynomial, formal polynomial in this algebra A. And we evaluate this polynomial on the spectral projections of the spin operators. And the question is, how would the resulting operator behave in the semi-classical limit? So I didn't talk about so why is the word semi-classical appears here, but sort of the representation theory of SU2 and the spin operators, they can be viewed as right. So they are, I mean, they are a quantum model. So they are the model spin operators and the spin angular momentum. So there is also a classical model. This classical model is given by just a two-dimensional sphere. So so as D goes to infinity, we sort of expect this matrix algebra to approximate the algebra of smooth functions on the sphere. So this can be made perfectly precise. So just this is really just geometric computation, etc. So, but I will not talk about this because I mean we don't need this machinery because we're just doing representation theory, maybe even not that. So still we have these operators f of p1 and p3, and we want to know in what way would they behave as d goes to infinity. So d is the dimension, and as I said, we want to compare it with polynomials in random pairs of projections and see if they behave similarly or not similarly. And right, so here there is some motivation. So as I said, right, I mean J1 and J3. So this quantization picture, they correspond to the coordinate function, the Cartesian coordinate function on the sphere. But so in that sense, they can be viewed as very good quantum observables. On the other hand, so smooth. So there is this word non-smooth here. So I'm just saying that these spectral projections they cannot be viewed in the same way as sort of quantum observables which correspond to smooth functions of two-dimensional sphere. So there is this story about algebraic properties of quantum observables, etc., which is relatively well understood for just smooth functions when we quantize them, and here there is sort of really different algebraic behavior because these are not observables coming from smooth functions. But also, I mean, just pairs of orthogonal projections and polynomials in pairs of orthogonal projections. So they can appear in the context of quantum mechanics. So the examples can be made. So right, so I already jumped to the simulations. So let me see if it makes sense. Right. So here we are considering the operator norm of a very specific bivariate polynomial. So the commutator. So just and I will mostly focus on the commutator. So we take the commutator of these two spectral projections, P1 and P3, and we consider the operator norm as a function of d as d grows to infinity. And this picture, so to me it is sort of strange. So I will try to explain it. So first of all, I want to say that for any two orthogonal projections, we have the following fact that the operator norm of the commutator is not greater than 1/2. So what this means that essentially when the dimension of the representation, so when the dimension of the space equals 4n plus 2, we get that the operator norm is really the maximal possible value. So this is a line of green dots. So this is the maximal possible value. And what I will soon say is that in fact the limit here is 1/2. So all of these four sort of distinct graphs in fact converge to 1/2. But while when the dimension is 4n plus 2, we get a constant sequence, which is constant and equals 1/2. For other dimensions, we get a sequences that do converge to 1/2, but of course do so slowly, and so on and so forth. Another thing to comment that actually this, so the case for, when the dimension is 4n plus 2 has been proven by Professor Kulturovich, who is my advisor here in Tel Aviv. So it is shown, and it is not too difficult, just by some, okay, so just rather straightforward. So it's shown, it's proven indeed that in this case the value is 1/2. But otherwise, the fact that this graph decomposes to 4 subgraphs, so it is unproven, and really this behavior that the operator norm depends on the dimension in this way that appears here, so it is entirely unproven.
How did you do the simulations? I mean, you say that you are doing simulations, but these are numericals, or?
So MATLAB, numerical simulation. So
okay.
We here, I mean, so this project started in my second degree partially because there are matrices here, so we can just really work with matrices and do simulations for them, etc. So
Okay.
So yes, so these are the simulations.
So you say that the theorem, that what you suspect is that it's always 1/2 this limit.
Yeah, so the theorem would be that it goes to the maximal possible value, even the lowest graph here. But the conversion rates, unfortunately, I don't know, and it is I conjecture that it is quite slow. That it is squared, so as 1 over squared logarithm of the divergence. So, but I will maybe say a few words about it later.
Okay.
So let's compare with random projections. So for random projections of the same rank, so we see that the norm sort of concentrates very quickly near the maximal possible value. And really the graph looks totally different. So just looking at these graphs, of course, suggests that the pairs of spectral projections of spin operators are somehow different. And random projections, obviously the graphs look really entirely different, even though in the limit the operator norms are 1/2 for spin operator for the spectral projection of spin, and here also the operator norm is with very, very high probability 1/2, or almost 1/2. So now the first theorem is as follows. So I already sort of said what the theorem is in the case of the commutator. So let's consider it in orderly way. So I will denote by omega n the product of Grassmann manifolds. Here I'm just looking at the orthogonal projections on spaces whose dimension is 1/2 the dimension of the ambient space. Okay, and this will be important because then afterwards I will play a game when I will look at the orthogonal projections whose rank are the proportion between the ranks of the projections in the ambient space will be smaller than 1/2. But now we are looking at the projections whose ranks are 1/2 the dimension of the ambient space, and we denote I and F just the expected value of the operator norm of a polynomial, so the operator obtained using the polynomial in the projection. And the theorem is as follows: that in this case, so when the proportion is 1/2, there is this constant. So given a polynomial, there is this constant which depends. It is determined only by the polynomial, such that this expected value in the random case and the particular value for pairs of spectral projections for spin operators, if we take the limits, we get that they agree. So in the limit they agree, they both converge to this constant MF. And this MF is a universal upper bound for the operator norm of the polynomial when evaluated with any arbitrary orthogonal projections. So here I'm relying on this theory of two projections, which is this story that has been researched for like, I don't know, 70 years or something. So there are results really from middle 20th century, so the 40s and 50s. And so some people looked at two projections. So there is this story which is sort of cute, and I'm really using it very, very much. And this type bound, this bound is tight because, for instance, so this is essentially a two-dimensional phenomenon. So there is this concept of angles between subspaces, and really this bound can be realized just by looking at orthogonal projections on one-dimensional subspaces. So provided they have the right angle between them, this will cause the operator norm of the polynomial to be maximal. So this is this constant MF. It is really the maximal possible value for the operator norm of the specific polynomial when evaluated on orthogonal projections. Okay, so this is sort of the first comparison. But now I want to sort of convince you that I mean, probably you suspect already, but that in fact the random case and the case of spin operators are not at all alike. Right. So, but before that, I just want to say that really this whole project grew from questions by Professor Ood Shabtai in the Hebrew University. So, really, I mean, I'm very thankful to him, and he essentially said that what happened in the theorem should happen. So, so really, yes. But as I said, this is the previous theorem is in fact so it is atypical when we look at projections whose ranks are smaller than 1/2 of the dimension of the ambient space. Then we will get that the limits do not agree. So the limit for random projection will be smaller in general than the limit for the spectral projections of spins. And as I said, these spectral projections are quite different than random projections. And I will not have much time to go into the proofs, so I just want to say a few, just 2 sentences. So there is the case of pairs of random projections has been considered in the literature on random matrix theory and so on. So much is known. I don't think that the specific things that I did here was known, but it really relies very much on existing results because I mean on the basically the behavior of this operator PQP when P and Q are random projections. The behavior of this operator is is quite well understood, and then this operator sort of determines everything. So here there are results from random matrix theory which are very powerful. And in the case of the spectral projections of spin operator, so the proof basically goes by calculating calculation and mainly asymptotic estimates of the matrix coefficients of one projection, P1 in an eigenbasis of J3. And the point is that this matrix entries they converge to Fourier coefficients of an indicator function on the circle of a certain interval in the circle. So there is this whole story with Fourier series here and things like that. And then using classical results about the Hardy spaces in the circle, the proof sort of follows. So this just a few words about the proof. So now, as I said, I want to consider projections whose ranks are proportionate to less than 1/2 of the dimension of the ambient space. So just for conciseness, I will look at not all the polynomials. So let me say it precisely. So first of all, C of the W will be just algebra of regular standard commutative polynomials, the commutative algebra. And I will look at polynomials which once you replace the non-commuting variables to commuting variables, they vanish. So this is a technical condition. So there is a general result for polynomials, but it's really just adding some more lines which are not very interesting. So I will just look at these polynomials when you replace a non-commuting variables into commuting variables, which still satisfy these properties of projections and the polynomial range. Okay, so now I think I can state sort of the 2 really more general main results. So the first one is for the random case. So now we know this omega of n alpha as a product of Grassmann manifolds, where now we are considering orthogonal projections whose dimension, whose rank is proportional to alpha times the dimension of the ambient space, where alpha is now allowed to be really less than 1/2. And aside from this, we're doing everything the same. So we take polynomial f, and then we evaluate it in random projections, and we take operator norm, and then we take this expected value of this random variable. And the result is that there is a dependence on alpha. So we fix this polynomial in the kernel of this sort of abelianization map, and let us denote this lambda alpha to be 4 times alpha times 1 minus alpha. And the thing to notice here is that lambda alpha vanishes when alpha, lambda alpha vanishes when alpha grows smaller. So what happens now is that there is this continuous function psi f, which is in fact piecewise smooth. It is determined entirely by f, and it vanishes on the endpoints of the interval 0, 1. And this was so for this reason I required to take polynomials from the kernel, but never mind it. And such that this integral over here, so the expected values, so in the limit, it just converges to the maximal of this function psi f on a sub-interval of 0, 1. So this sub-interval is really in general a strict sub-interval. So if we take alpha to be smaller than 1/2, it will be a strict sub-interval. And so, right, and so the maximum of psi f on this interval is potentially strictly smaller than mf. And mf is, because mf is just the maximum of psi f on the entire interval. So this is sort of the story here. So if we take pairs of random projections whose ranks are very, are smaller than 1/2 of the dimension of the ambient space, we get that the expected value here of the operator norm becomes smaller and smaller as we decrease alpha. And right, and in the endpoints, because psi f vanishes in the endpoints and it is continuous, so when alpha is very small, we will get that in the random case, the limit is very small. But this will not be the situation for spectral projections coming from spin operator. So as I said, when alpha is very small, in the random case, the operator norms of polynomials tends to be very small. But when we consider pairs of spectral projections of spin operators, and here I'm looking at any polynomial. So now, so let's do this carefully. So we consider intervals. The left endpoint is 0, and the right endpoint is just alpha d, so that we manage to grab exactly alpha d elements of the spectrum of the spin operators. Okay, so this to have a spectral projections which are of the right rank. So the rank will be right alpha d here, floor. And what we have is that when we evaluate our polynomial on these spectral projections, we still get that the operator norm converges to this maximal possible value. Okay, so in particular, so the conclusion here, so it has two parts. The first part is I already said it is sort of immediate that. By continuity, if we take alpha very small, so I alpha f will be just the maximum of this continuous function on a very small interval, and mf is the maximum of the very same continuous function on the entire interval. So mf will be really larger as soon as the point in which psi f achieves the maximum is no longer in this very small interval. So this I already said. So the limit for spin operators will be larger. So this is for every polynomial. But and another thing is that for every alpha, we can find polynomials such that there will be a discrepancy. So for every alpha, we can find a polynomial such that in the random case we'll get a certain limit, which will be smaller than the limit for spectral projections obtained from spin operators. So in this way, we can really rigorously say that pairs of spectral projections of spin operators, in some senses, are really unlike random pairs, and really so this can really measure theoretically be formulated very precisely. So just yes. Okay, so now let's see some simulations for this. So remember that in the random case, as we look at projections with small rank, we expect things to become smaller, and in the spin case, we expect things to remain large. So now here is a sort of strange graph to my eyes, but let's not consider for 1 second the top line. So this is just again the same polynomial, namely the commutator. So we're just considering the commutator of spectral pairs of spectral projections of spin operators. and we're plotting the operator norm. But this time we're looking at a projection whose rank is right alpha times the dimension of the entire space rounded down, with alpha equaling 1/20. So what we see is that, as the theorem promised, indeed the operator norm converges to 1/2. So this is the only thing the theorem promised. Otherwise, the theorem didn't say anything about this image here. And of course, we can see lots of other stuff in the image, and this other stuff is not proven. But okay, but at least we know that things go to 1/2. And but okay, but let's say a few things about a few words about what I really have no idea how to prove. So first of all, there is still this decomposition to sort of 4 cases, but according to the dimension of the representation. And I really find it sort of hard to explain this. But what's even more mysterious to me is this general phenomenon, which is just evident numerically. When we take alpha, which equals 1/4k, where k is some positive integer, then the graph decomposes mod 4 to sort of piecewise nice functions. So it looks as if we have 4 functions which are sort of piecewise, almost continuous, or something like this. And the pieces, they are of length k. So this is strange. So here we have 1/20. So k is 5, and indeed we see that there are 5 dots in each piece, and this is a general phenomenon. So if we take alpha equals 1/16, we get these pieces will each contain 4 dots. So yeah, so this is a phenomenon which on one hand it is really cute to my eyes, but I don't hope to prove it in the near future, but maybe they will be surprised. So, yes. Okay, but in terms of the theorem predicted that indeed this graph should grow to 1/2, and but not monotonically, not at all. Yes. And for random projections, so we expect things to be smaller when alpha is small. So here we take alpha to be again 1/20, and we see that so in just sampling random pairs of projections and then taking the commutator and plotting the operator norm. And we see that there is a sort of convergence in some appropriate sense, but to a value which is strictly less than 1/2. So the value can be computed explicitly because, so I will soon say why, but basically this function psi f, it admits a nice formula in terms of the polynomial. So for commutators, psi f is really just, psi f is just square root of t times 1 for commutator. So indeed, for random projections, we get something smaller. Yeah, so these are sort of the main results, mostly the main results, and maybe I would say a few comments. Right, so as I said, there is this story theory of 2 projections. So I've been using it for both cases. And basically, when we take polynomial from this algebra A, so we can uniquely write it as written here. So we have this constant term, and then we have these terms which begin with x and end with y, terms which begin with y and end with x, terms which begin with x and end with x, and terms which begin with y and end with y. So these are the polynomials that we're considering, and then psi f has a simple formula in terms of this polynomial. So everything in principle can be computed. Right, so basically the operator norm of a polynomial in these 2 projections, it is just given by evaluating psi f on spectrum of the product p times q times p. So so this sort of explains quite a lot. And there is another comment here, which basically there is a sort of a geometric picture where, as I said, where there is this concept of angles between subspaces. So they are called sort of canonical angles or principal angles. And they're really defined using the inner product. So just S angles sort of should be defined. And the spectrum of this operator PQP is equals so the eigenvalues are the squared cosines of this sort of angles between the relevant subspaces. So this is another comment. Yes. So some examples. So as I said, things can be computed quite explicitly. So if we consider polynomials of rather special form, so which are constructed using the univariate polynomial, then this psi f, which, as I said, so it gives us, given any two orthogonal projections, it gives us the operator norm of the polynomial when evaluated in this projection. So this psi f is given here, and in particular for commutators, or more generally for this kind of bivariate polynomials as here. So we have this kind of psi f. So everything can be computed. This is this sort of the message here. And then once we compute, we can also try to check if numerically things work. So numerically they do work. So these are random projections. So here I took the dimension to be 1,000, and then I plotted the operator norm of the commutator of random projections, the function of alpha, where alpha is the proportion between the rank of the projections and the dimension of the ambient spaces. Again, I recall, and we see that already for n equals 1,000. So the operator norm is really quite close to the theoretical limit, to the theoretical value of the limit, which is just a maximum of psi f of this interval. Yes, so this is really most of what I wanted to say. For spin operators, as we consider projections of as a function of alpha, and we increase, so the operator norm is a function of alpha, and we increase alpha, we get this rather strange graph. And as I said, everything here should go to 1/2 as we increase the dimension. But right, so even if we consider this, so we need yes, so everything goes to 1/2 as the dimension goes. But for fixed dimensions, the behavior is to me quite strange. And really the last result that I wanted to talk about, and yes, I probably should have said a few preliminary words about it, but somehow I didn't manage to put it in the slide. So as I said, the key player in this whole story of two projections is basically this operator over here. So because the spectrum of this operator determines the operator norm of all polynomials in these two projections. So given any two projections, P and Q, we consider the spectrum of P times Q times P, and this spectrum will determine the operator norm of any polynomial in this projection. So it is natural to look at this operator, and its spectrum, in the case of spin operators, behave in a sort of dramatic way. So let's try to make sense of the theorem. So one thing to note here is that dimension of so we are considering projections of rank alpha times the dimension of the ambient. So what I'm basically saying here is that when we look at this operator, almost 1/2 of its eigenvalues are very, very close to 0, and almost 1/2 of its eigenvalues are very, very, very close to 1. And then intermediate eigenvalues, there are logarithmically many of them, at most logarithmically many of them. let's look at the picture, and this really says more clear perhaps in the formulation of the theorem. So again, we're considering the spectrum of this consecutive product of non-commuting spectral projections of spin operators. And so the spectrum naturally should be a subset of 0, 1, right? So this operator is right. Its norm is 1, and then so on and so forth. I mean, less or equals than 1. And we see really that, so here the dimension is 2000, and here the projections are of rank 1000. So there are 1000 eigenvalues with multiplicities in general, and we see that really almost 500 of them are very, very close to 0. Almost 500 of them are very, very close to 1, and there are visibly just 4 intermediate eigenvalues. And these eigenvalues, they are the ones that cause sort of the operator norm of the commutator to go to 1/2. So these intermediate eigenvalues, while their number really grows very, very slowly, they are the ones that are responsible for this maximality phenomenon, in which the operator norm of every polynomial goes to the maximum possible value, because we get for this operator here eigenvalues which are close to 0 and eigenvalues which are close to 1, but crucially also eigenvalues close to any number between 0 and 1. And this is not the case for random projections. So random projections, the graph is I mean, sort of nice, but here we are looking at the case where the random projections are of rank, which is 1/2 of the dimension of the ambient state. But if we looked at the smaller ranks, then we would no longer have a spectrum which goes from 0 to 1, but only from 0 to some smaller number, and that's so. But anyway, things are quite different from spin operators. And so maybe one or two less things to say. So first of all, about this behavior of the theorem. So this kind of behavior we have when we have only logarithmically many intermediate eigenvalues and then very many eigenvalues which are very, very close to 0 and to 1. So this kind of behavior has been observed before and is actually quite important for applications. So it is known, so in sort of applied mathematics, Slepian spectral concentration or something like this. So there are flat spheroidal wave functions and all kinds of families of functions, and which are, I mean, okay, so there are these flat
We don't know this thing, Ood. What is this Slepian? You say these applications to apply mathematics. This is like, what is this?
Yeah, so this, so I did not include the slide properly, but I can explain it quite simply as follows. So,
thank you.
The original context of this is just usual Fourier transform. So let us consider in L2R band limited functions and space limited functions. So basically, we have two projections in L2R. One over just the multiplication operator by some interval, and then the multiplication operator by some interval, but conjugated by the Fourier transform. So just let's take the same interval. Why not? So these are two orthogonal projections on L2R, and so we can sort of play the same game about this orthogonal projection. So let's say this one is P and this one is Q. So originally, so in the 60s, the problem considered by Landau, Pollack, and Slepian was to find say functions f in the image of P, which are sort of maximally concentrated. So the Fourier transform is sort of maximally concentrated in the interval, mean interval. And of course, the Fourier transform cannot be entirely concentrated there because because this function is completely supported. So so this was the original problem, and this has many applications, as it turns out. And I'm not very familiar with applied mathematics, so anything that is applied is something that usually I don't understand.
This is what will publish your paper, the applications. This is what will get your paper accepted. So it's good.
Yeah. No,
So you mean this could have applications to, I don't know, signal process or something like that?
Yes, signal processing, because the eigenfunctions of PQP, so they are called Epulator wave functions, and they have many good properties as functions as a basis for band limited functions. So space limited functions. Sorry. So really, this is just by reading sort of abstracts and introductions. So the details really I can't say much.
Wow.
And of course, if we played it with this game with Fourier transform on R, so this was the original. So this guy Slepian, so he has been working in Bell laboratories in the 60s when he did this. So this really came from applied consideration. And then why not consider Fourier series? And then there is also finite Fourier transform, and the same game can be played over there. And basically, we want to obtain these functions which are both them and their Fourier transform are localized. And of course, we have to pay some prices. So to put it precisely, basically, the story in general terms is always to find eigenfunctions of this operator PQP. And if we look at the graph here, so the eigenfunctions corresponding to eigenvalues which are very close to 1, they are really localized with respect to both orthogonal projections, because first of all, they are of course localized with respect to P3 because they are just in the image of P3. They're eigenfunctions, but they're also localized with respect to P1, because how much of the L2 norm, how much of the norm did we lose when we acted using this operator? Really didn't lose anything. So they have eigenvalue which is almost 1. So they are sort of localized with respect to these two orthogonal projections. And since these projections are non-commuting, well, I mean, so there is yeah, in general, I mean, yeah, so maybe we could not find. So if there is no Southwest and Wheat projection commute, and really there is no optimal localized, so you cannot get absolute. Okay. So I see that I've also already jumped ahead. So maybe I will skip the next step. So really, these are just remarks on the convergence rate, and I just want to say basically that, I mean, okay, just that this picture over here results in slow convergence rate. So this is the first thing I wanted to say. Basically, because because we have very few eigenvalues over here. So how slow? So for many polynomials, the convergence rate will be not faster than squared logarithmic. So this is what's written here. For some of them, should be for most, but okay, but so the convergence rate for many is for sort of most polynomials is not faster than squared logarithmic. And the last thing that I wanted to say is that just to show this picture over here and say a few words about it. So as I said in the beginning, so we're really doing linear algebra, but we'd also like to think about sort of quantization of the dimensional sphere. And then, so what we did in the past, so we take this commutator, whose operator norm, as I said, goes to 1/2. And we take an eigenvalue, vector corresponding to maximal eigenvalue. And then, as I said, so right, so then, okay, so this can naturally, so the representation can be realized using bivariate homogeneous polynomials, but also just polynomials on C. And then we can use orthographic projection to take them to the sphere, so the eigenvector basically is a function on the sphere, on the two-dimensional sphere. And then we can plot its modulus. So, and we see that the modulus, it really concentrates, so the eigenvectors, in some sense, it concentrates about these boundaries of these two hemispheres. There is probably this story here. So we suspect that these spectral projections, they are observables which are somehow related to classical domains. So if the spectral projection is on the positive eigenvalues, then it should somehow correspond to the domain x1 greater than 0, to the hemisphere. But this is not precise what I'm saying right now, although there are some works going in this direction, but I don't have, I have no knowledge of precise results about it. So yeah, so this is a sort of a geometric story here that it is evident numerically, but not rigorously. So this is also something that I wanted to mention. So I think, yeah, I think I will stop here. So really, thank you very much for listening. And hope it was interesting.
Thank you.
Thank you.
But you have 7 more slides.
Yeah, so I mean, yeah.
What are the mysterious slides?
So they are backup slides because always I fear that. But actually, I no longer fear it actually because.
If somebody asks you for the detail of the proof, then you.
Yeah, so maybe some details if there are questions. So, but I already said the details. So matrix coefficients go to Fourier coefficients and things like that. So, yeah, so there are details about it. So I mean, here there is a conjecture about so sort of explaining this picture over here. So as I said, if spectral projections correspond somehow to domains in phase space, then basically the conjecture is that if the boundaries of the domain intersect transversally, then we will, and the dimension, there is a dimension is 2 dimensions, so 2-dimensional manifold, so we will get the behavior which is similar to the behavior described for spin operators, and if the boundaries do not intersect at all, then everything goes to 0. And numerically, so as far as I would check, this conjecture sort of holds, but I've only checked very limited cases. So basically for observables constructed using this spin operator. So in generality, for an arbitrary 2-dimensional quantizable manifold, I wouldn't know what to do, but numerically it has been sort of checked the story in this case, but it's really limited. And then yeah, so this was one comment about this sort of conjecture about domains in phase space. And yes, and another comment, since you reminded me, was that I have a slide. So another comment in the slide, which maybe is worth making, is that I've actually played this game for more quantum observers. So for position and momentum operators in L2 of R, and then for operators of L2 of the circle. So, but which are sort of constructed using position and momentum operators on the circle. So sort of Y quantization of the cylinder. So they're just, but it is really Fourier series and so in all examples that I've checked, which were all really just position spectral projection coming from position momentum operators, or the analogs for Fourier series, the circle, and for finite Heisenberg groups. So this is just finite Fourier transform. So a number of cases which are easier and sort of in some senses less interesting, perhaps, but and in all cases the behavior was the same. This maximality result, and of course this Slepian phenomenon in which there is clustering of eigenvalues near 0 and 1. So it also happens. This has been discovered by Slepian and this fellow. So yeah. So as far as I know, the conjecture of this being sort of a general behavior, so it has been verified numerically in a very limited way. But yes, and also for a number of other cases, it is also sort of hold for this. Yeah, also remark.
Very good. Well, Pau is the chair, so I'll let him be the chair. We don't hear you. You have the microphone problem.
Well then, I can take up the mantle problem.
I don't know what happens, Pau. We don't hear you. No sé qué pasa. Ara.
Okay. So let's thank God again, and now because I think we did not clap, and this is no.
No, we didn't clap. This is very bad. Let's clap.
Thank you.
Thank you very much.
And now it will be the time for questions. If any of us has a question, it's the moment to ask.
Well, I mean, you were saying this. I mean, you were saying this towards the end, no? The applications to this quantization in the sense that, for instance, Pau precisely is working on, no? With this idea of semi-classical approximation. I mean, do you have something to say about the potential application of your result?
In the context of semi-classical.
Yeah. Because it also has applications to quantization, like different models. I mean, does this just give you or justify something in semi-classical analysis or semi-classical approximation? Or
no, so I mean, at this point, so the project grew as follows. So Professor Potorovic Leonid, he wanted to quantize indicator functions and really to quantize pairs of indicator functions and check so sort of the correspondence principle for them and indicator functions. So we can't say much about their quantization, and so it was led to consider smooth indicator functions and right, and then there are some results, but okay, but and this was sort of a toy model in the sense that, okay, we don't know much about quantizing indicator functions, so let's just instead of quantizing the indicator function of the hemisphere x greater than 0, let's just quantize x and then take the spectral projection. So this was the original motivation. And then at the moment, I really, as I mean, clear from my talk, I really can say very, very little on the general case. And but for me, it is interesting to look at just one spectral projection in the general case because there is this story here. Because I mean, in at least I mean, there is in topic quantization, so there is a Bergman kernel. And the asymptotics of the Bergman kernel are very important to proving all the properties, etc., etc. But so for me, I mean, if we have just a function, I mean, so I mean, if we took its spectral projections and whose rank is alpha times the dimension of the ambient space, and we increase alpha, so eventually we just get the Bergman projection. And so I'm really interested in the asymptotic behavior of spectral projections and as a generalization, right, of the asymptotics of the Bergman kernel and things like that. But at the current stage, I can say so little about the specific case of spectral projections of spin operators. That I'm not sure. I mean, it interests me very much, the semi-classical questions, but I really can't say.
But this is nice. This is really
I mean, there are some works, right, about, so there is some work by Professor Steve Zeldich about a single sex projection, which, as I said, it is an interesting topic to me by itself. And indeed, he related a certain quantity, sort of, which he called the density of states. Never mind the precise definition, but indeed related its behavior to the classical domains that we would expect it to be related. So, yeah. So there is some work. But here we are also talking about two projections, and yeah. So I mean, there are all kinds of things. But as I said again, so this just I can say very little in terms of texture.
Yeah, so Saldit has been working on that and his collaborators, yeah, several people. But I think that this is very interesting. You told us that you started to work on this on your undergraduate, or
No, in
maybe
the second,
Kasdan puts you this as a problem of as undergraduate, or I
no,
understand.
so for a second degree, and but it was only the operator knows the commutator. So
Okay.
yeah, so yeah, the first image that I showed. So it was, but so Leonid, my advisor, so he saw that it would be an exercise for like a week or something, or maybe less. So, but then I came after a while, and I said, yeah, I didn't know. And then there was this postdoc, Johan Top, maybe
Who
you
was
know
there
him.
working on
And
this?
yeah, so he was working with me, and then he said, well, I'm not sure either. And then it turned out, so so the commutator, right? So maybe I'm not. So the commutator, I'm trying to move the slide here. Never mind this. Right. This slide is of course important. So the commutator, there is a matrix of the commutator, and the matrix is of the form something like this, y and minus y. Like this. So in my second degree, so basically mostly Johan, but yes, was able to compute one matrix element, so the asymptotic limit of one matrix element here, and this shows that it goes to 1 over pi. So this was basically sort of my master's thesis, was that the operator norm of the commutator it is greater than 0. So it is sort of, let's say, yeah, the lim inf is I don't know, greater than epsilon, greater than 0. So this was yeah, so this was the second degree project, and really the matrix coefficients, they are terrible combinatorial expressions or sums of products of binomial coefficients which come from special functions, etc. So in the first degree, second degree, we found one matrix coefficient with the combinatorial expressions were terrible, but somehow manageable, and managed to prove that it goes to 1 over pi. So this was in the case that d equals 4n. The other cases, so d equals 4n plus 2, as I said, Professor Petrovic, he proved that the norm actually equals 1/2, and then the other cases I did, but which were easier. So this was a second degree, but and then but I really wasn't satisfied, and I was sure that to some extent more can be done. And then indeed, so in my PhD, so I did this. I found a good expression for all the matrix coefficients, and were able to find limits of sufficiently many of them. So to show that actually there is some sort of convergence to really an operator on L2 of the circle. So just yeah, so classical Toplitz's operators in the circle, and Henkel operators in the circle, and really classical yeah, Harvey space theory.
So when are you defending when are you defending your thesis? When
yeah, I mean, so I still do not have a date. I mean, so I've finished doing everything really quite a long while ago. So I need to write things down, and I mean,
so you didn't submit the thesis yet. You didn't submit.
I didn't submit it.
Okay.
But this is sort of the less. I mean, yeah, the less thing.
But this is the most important thing. Once you submit the.
Oh, definitely. No, I'm not feeling good about my time. My time at all. But yeah, I mean, so yeah, so I mean, the works are published in paper, so I'm not fearful that much about finding sort of problems, but still, writing needs to be done, and it takes time. So I mean, yes, yeah. But really, this is yeah. I hope to, I mean, put a pause to my life for a couple of months, starting sort of from next week or something, and then write everything down properly.
A couple of months. You are an optimist.
No, I mean, start in a couple of weeks, and then a couple of months definitely. Yeah.
But you have many papers already written. What I saw.
No, I mean, I don't have many papers. So this one
you have 3 or 4
today. It is 2 papers. So this is a content 2 papers. I mean, there is an earlier paper, but this will not be part of the thesis, which I did with many other people, but it is
Okay.
very different, totally different stuff. It's just symplectic dynamics and Hofer's metrics and things like that. But no, but this stuff is in 2 papers, but still,
Yeah, I
it
saw
will
this
take
thing of the
me
Hofer's metric.
plenty of time to make it into the thesis, I'm sure.
Okay, that's nice. So this is a good example how a problem of the master takes you everywhere. This is what here there are 2 students, Pablo and Alberto, who are doing their undergraduate thesis at this moment, and
Very nice.
maybe they end up. Yeah, Alberto arrived a bit late. I don't know, Alberto, if you could follow a little bit because you arrived more or less. Alberto is doing a very complicated undergraduate thesis with Sergei Gukov in Caltech, but he's in Barcelona because of COVID, right? Well, I mean, because he's starting in February. And Pablo should be in China now, but well, you know, it's very complicated.
Yeah,
with
definitely.
with polyaracetiquine. And he also has to face some problems that look very, very easy, but then they are difficult.
Yes, yes, definitely. I mean, so yeah, so I mean, in this case, so like, so really finding the norm properly would sort of mean finding the spectrum of this PQP operator that I told you about. And in the case which Slepian considered, this has not been done. So I mean, I'm very doubtful that I would be. So yeah, so I mean, it was supposed to be an exercise, and then there are sort of open problems going to the 60s that are really
but this is
equivalent to this exercise. So, but still, I mean, it means that but still things could be done. So I mean, of course, I'm very happy that I received this exercise.
Yeah, exactly. Exercise.
Yeah.
Yeah, I don't know other questions. Well, I mean, I am not the chair. I mean, I am taking your position.
But I have to say, sorry, that I'm interested in the part of passing, because you're working with operators at already at the beginning you talked about quantization, but you passed to the operators part. But we're at the point that we have worked quite a bit with the first step of quantization, but we lack the part of working with the operator. So with Eva, I think we should go at some point to the working with the operators, and maybe we can compute eigenvalues and other things of operators in manifolds with boundary, for instance. So this is a point we are missing for now, but I think it would be interesting.